Good afternoon. I guess we will get started. It's a great pleasure to welcome all of you to this special edition of the KAAPI with Curiosity lecture series, which is a flagship outreach activity of ICTS, which has been running for the last several years. We have been running this activity in collaboration with the Jawaharlal Nehru Planetarium in Bangalore at the planetarium site. But since the pandemic outbreak a couple of years ago, these public lectures are being run online, but we are still hoping that in the near future, we'll be able to go back to the original mode of these public lectures. Today, we are also celebrating the National Science Day. So I'm particularly excited to welcome my colleague, one of the most dynamic young astronomers of our times, Professor Varun Bhalerao, to give this talk. So let me very briefly introduce Varun. Varun is a faculty member and assistant professor at the IIT Bombay. And several years ago, he did his undergraduate degree at the IIT. And after that, he did his PhD at the California Institute of Technology, Caltech, under the guidance of Sri Kulkarni, one of the most important astronomers of our times. And during his PhD, he contributed to several very important projects in the cutting edge of astronomy, including the New Star project, New Star satellite. And after his PhD, he was a Vaidya Rai Chaudhary Prize postdoctoral fellow at IUCAA, the Inter-University Center for Astronomy and Astrophysics in Pune. And during this period, he also contributed to India's very first astronomy satellite, the AstroSat, which was India's first astronomy mission and the multi-wavelength astronomy satellite. And in the last few years, he has been an assistant professor at the IIT Bombay, where he's building up a very large and dynamic group working on very different aspects of astronomy, in particular transient astronomy. And today he's going to talk about this very upcoming and very active emerging area of astronomy called the transient astronomy. So before I invite Varun, let me make a few bookkeeping announcements. If you have any questions, please type those questions in the chat box. At the very end, our outreach coordinator, Professor Anupam Ghosh, will take these questions on behalf of you. If you would like to ask your questions directly, you can raise your hand in the Zoom. People in the YouTube also, you can type your questions in the YouTube chat window. So without any further delay, let me invite Varun to give his talk about taming the transient sky. Varun, the floor is yours.
Thank you very much, Ajit. Hi, everyone, and wish you a very good evening and wish you a very happy Science Day. Usually here I would have started with talking about the background of Science Day itself, but I realized that it's evening by now. You have probably stumbled across Professor C.V. Raman's discovery and the subsequent Nobel Prize and so on several times. So I'm going to talk to you directly about how we tame the transient sky. So what do I mean by the transient sky? You've been looking at this video, and what you're seeing here is at the bottom is a nice telescope. That's our Growth India telescope that we have here. And you can see the Milky Way galaxy rising in the background. We'll talk a lot more about this telescope as we go through. But mainly, if you are fortunate enough to still be at a dark site where you see the Milky Way, you pretty much see it the same way no matter when you look at it, right? If it's up above the horizon, the Milky Way looks the same today as it did 10 years ago and will probably look the same 10 years from now. So when we are talking about the sky, we usually think about it as something that is extremely static, something that does not really change a lot over time. And our mythologies also refer to things like this a lot. The sky is unchanging. The reason really for that is not a problem with the sky, but a problem with, or a limitation rather than a problem with us. Humans live for maybe 100 years or so. Stars live for millions to billions of years, which means that something that changes in those stars also can take a lot of time to change, and we usually don't see it. But let me give you a bunch of examples of what actually does go around in the sky. For example, stars themselves are actually born, they live a life, and then they die. And let me show you a nice animation of those. So what you see here are images, actual images of the sky, and now you start seeing these new dots popping up and then fading out. These are all actually supernovae explosions in the sky. So supernova is a massive star that blows up. But what you can see here is that over the period of several months in this small part of the sky, where I have shown the full moon here for comparison, there is a lot that is going on in the sky. There are a lot of stellar explosions that are happening. So let's try to understand these a bit better. Okay, so I'm going to show you just one single explosion. So this is a galaxy called NGC 2422. It's a very nearby galaxy in the cosmological sense. It's only 80 million light years away. And I'm going to show you something that we saw in 2015. So what actually happened in this galaxy happened 80 million years ago, but we talk about it as if it happened in 2015. That's because that's when we saw it. So think of it as if you're watching a recorded sports match, or if you're watching a movie. The movie was probably shot over months, but you see it as if it's happening right now. And then when you're talking to your friends about it, you talk about it as if things happened in that order. Okay, so for us, this was supernova 2015. So keep an eye on this galaxy now. The galaxy itself is a spiral galaxy, but not a very tightly wound spiral. And now pay your attention to this red circle that you see at the center. And there you have it. Something suddenly became bright, and after a little time, it is fading away. So let's do this again. Now with a zoom in. Okay, so keep an eye on this circle. You can see there are a few bright objects. Some of these are foreground stars. This is a spiral arm of the galaxy. What you see here is some dust. But now let's look at the zoomed in version. Oops, it restarted my video. Let's send it back to that point. There we have the full galaxy visible again. And that's the supernova. You can see the time here is being marked. So this is a montage taken over a period of several months. And here it is again. You have nothing seen at that spot, and then suddenly a very bright star appears, reaches peak brightness in a couple of weeks, and then remains visible for several months. So what exactly is going on here? In this particular case, it is what we call a core collapse supernova. Okay, so a core collapse supernova is something. Here's another example, actually, data from the Growth India Telescope. I forgot I just put this in. So what you are seeing here is another animation. So in this case, we have zoomed in quite a bit. The galaxy would have been seen up here at the top of this. And you can see that this is data from 2020 from our very own telescope. And the time here going from around September to around December. And again, you see a bright star that appears there, brightens up, and then over time slowly is fading away. So what's going on in all of these cases is that these are massive stars dying in explosions. So the way a star works, the way a star generates heat, is that at the center, there's nuclear fusion going on. So there's immense pressure from the outside, and there's a lot of fusion going on in the inside. It's like thousands and thousands of nuclear bombs exploding every second. And all of that pressure is really balancing that star. Now, this core collapse supernova is something very strange. When the center actually runs out of fuel, what happens is that the entire star, because there is no heat being generated, it cannot hold. You know that stuff expands on heating. Now, if you stop generating that heat, it's going to cool down and the core collapses. And as a result, suddenly there's a lot more material in the center. It again starts undergoing fusion and the whole star blows up. This core collapse supernova, over its duration of just a few months, can output more energy than the sun will output in its entire lifetime. And these happen to stars which are 8 to 10 times heavier than the sun, going all the way to 50, 60, even 100 times the mass of the sun. So this is just one of these many transient phenomena in the universe. We call them transients because these are objects which exist or are seen for a short amount of time. Here's another one. This is something called gamma ray burst. Again, there are two types in these. I'm going to show you one where this is again related to a supernova. So now I have a large blue star. And rather than that massive supernova explosion, this is a slow motion animation of the start of the explosion. And here I'm playing it now. What happens is that this explosion first creates two extremely intense jets, which then rip through the entire star over time, and then it is followed by the supernova explosion. So what happens is that if you are an observer along one of mission in gamma rays, and those are called gamma ray bursts. A curious thing is that these were actually discovered by US satellites, which were checking if Russia was secretly doing nuclear tests. And they were very surprised when they saw signatures like a nuclear test, but coming from space. And it was the data was declassified later, and astronomers figured out that this is actually what is going on. What you saw at the end of this animation was actually that a GRB like this, a gamma ray burst or a GRB like this, actually ends up forming a black hole at the center. So this is one of the transients which is associated with a black hole, and everyone loves black holes. So let's talk about one more example of the. So these are called tidal disruption events. The black hole that I talked about a minute ago was a black hole that is maybe 10 times the mass of the sun. Okay, what I'm going to show you here is something that is done by black holes which are millions to billion times heavier than the sun. Okay, so I'm going to mark an arrow on the screen, and I want you to pay attention to the tip of that arrow. What we are going to show is that in this animation, there's a black hole, extremely massive black hole. We just call it supermassive black hole, not very imaginative in naming. And a star is going to zip past that black hole. What happens then is that the extreme gravity of the black hole completely rips apart that star. And here's what's going to happen. So pay attention to the tip of that arrow. And here we have it. The animation, there's the star, and the black hole is being shown by blue here. And all right, let's play that again. Okay, so there's the star that's coming in, and as it passed by the black hole, it got completely ripped apart into extremely long thread. It's no longer a star, it is now just a pile of dust and gas. And you can see that some of it is going outside, other parts of it are orbiting in a very small compact orbits. And these kind of things are called tidal disruptions. So just as the moon causes tides on Earth, these are extreme tides that were caused by that supermassive black hole on that star. And when it ripped it apart, all of this gas which is going out is actually glowing across all wavelengths. And we see this. These are detected in optical, these are detected in X-rays, and they actually allow us to study properties of these black holes. So understanding these kind of phenomena actually allow us to probe the most extreme circumstances in the universe. The universe does for us things which we cannot do in the lab. We cannot actually say, let me take up a large star, light it up like a Diwali cracker and blow it up. So we have to wait for these things to happen. And in these cases, we get to study the most extreme gravity, the highest temperatures, the strongest magnetic field, the most extreme phenomena in the universe. So I talked about supernovae and gamma ray bursts and tidal disruption events, but there's a whole zoo of transients out there. Okay, there are a lot of different kinds of events. It's as if the universe has said, hey, you want to study how stars evolve and die? Here's a buffet that is set up for you. You can go and sample whatever you want, have at it, and try to understand what's going on here. Now, when you're going to a buffet, you just can't go like that. You have to go well prepared. So what are the things that you do when going for a buffet? Well, let's look at the buffet 101, the basic things that you want to do. First is you never go alone. Okay, you want to go with friends. You want to make sure that you are ready for whatever the buffet is going to serve. Start with an empty stomach. Make sure that you're focused entirely on that meal there. And then you also want to focus on your favorites. If you try sampling everything, then you're not going to be satisfied. Your stomach's going to be full even before you actually could enjoy one particular dish. And you don't want to be getting up every now and then to go get water or something. You just send your friends to do that. So you focus on what's important to you, eliminate the routine tasks, have something else do those for you. So why am I talking about buffet? Well, the same rules actually carry over to studying transients as well. So when we want to bring friends, we actually assemble a large group of astronomers with various types of telescopes and different resources, so collaboration called growth that I'll talk about. And then we also want to make sure there is nothing else on our plate, nothing else on this in our stomachs as well. So we want a dedicated telescope which will focus on this particular activity. And not only that, we will have very well defined key science goals. We don't want to do every possible thing with our telescope. We want to say, here are the few things that we want to do, and those are what we will do. And then finally, we want to automate a lot. We don't want to keep doing the routine repetitive tasks. We want to do what is fun for us, which is the science, which is the interpretation. Okay, so let's look at all of these points one by one. So growth itself is an international collaboration that we set up several years ago. The reason for doing that is getting to study a transient is extremely rare. As I said, we cannot control when a supernova explodes. We cannot control when a gamma ray burst happens, but we want to be there and we have to study it when it happens. So in some sense, it's like getting one of these amazing nature photos or Nat Geo photos, right? So if you want to get into this follow-up challenge, you want to make sure that you're at the right place with the right time with the right equipment. Okay, so what do I mean? Well, it's quite obvious that if you have to photograph this tiger, you have to be there when the tiger got out of the water, and you have to have a good enough camera to do that. For transients, let's try to explain this again. Okay, so here's one of the cases where a global network is needed. So what I've shown here with binoculars are some of the places where some of the large telescopes in the world are located. And I've chosen a time when it is just after sunset in India. So what happens now is that unfortunately, all these telescopes, while they're of extremely good quality, they're all in daytime and they just can't do anything. So suppose there's an explosion that happens somewhere above India at that time. Okay. So as seen from this star, this is what Earth would look like. And you notice that all the locations where the large telescopes would have been are actually on the other side of the Earth. So if you are not in the right place, you're not going to detect anything. Not just that, you also need to be there at the right time. So let's take the same scenario again. And now suppose a transient goes up right above those telescopes, but it is daytime there. Then you are not going to be able to see anything either. So you want to make sure you have good coverage. If possible, you want to have some space telescopes in the mix as well. And you want to have telescopes that are geographically separated. You want to have a telescope here so that if these parts of the world are not visible or cannot see the transient, then we can. And with these goals in mind, we actually set up this transient observing group or this collaboration called GROWTH, which stands for Global Relay of Observatories Watching Transient Happen. All right, so that's quite a mouthful. The idea is that we have telescopes all around the world. We start with a large wide field telescope called the Zwicky Transient Facility located in California. If they discover something, then it's like a relay race. Okay, as the Earth rotates, the transient starts setting here, that part of the sky sets, but the same part is then rising in Hawaii, after which it would be visible in Japan, Taiwan, India, Israel, and then Canary Islands, and then back in the US. So as a result, we can hand off these observations saying, hey, this target is extremely interesting. We were observing it right now, but it's setting for us, it's rising for you, you take it over. And as a part of this, we set up IIT Bombay and the Indian Institute of Astrophysics Bangalore jointly set up this telescope called the Growth India Telescope. Okay, so here's another example of this growth network. So suppose I'm floating at some vantage point in space and the Earth is happily rotating under me. These are all the places where we have telescope partners that can actually do observations for us, right? And you can see that at any point of time, you're seeing not just one, but multiple sites. And which means that telescopes at all those locations could be seeing you if you were actually floating out in space. Now, there's something else that we have to add in here, though, that suppose there is the cycle of day and night, right? So let me put the sun on the left, and which means that the left side of the Earth will be having daytime and the right side here is going to be nighttime. So we actually are still sure that there are enough telescopes at any given point of time that have night, which means that those telescopes can still continue their observations. So this is the key thing about the growth network. And we have been immensely successful in studying these kind of transient objects with this network. As a part of this growth network, my laptop really doesn't want to go forward. Sorry about that. So as a part of this growth network, we have not just a network of telescopes, but also a network of people. And that is extremely important too. Science is not just about getting data, it's about understanding that data. So here's the IIT Bombay team, my students and postdocs that work on it. And here's the Growth International team. This was also a picture taken at IIT Bombay during one of our annual conferences. So it's all of these people using all these technology and tools all over the world that has managed to do quite a few cool things. And we'll talk about some of those. Okay, so finally, speaking of the right equipment for India, we wanted a wide field telescope because you want to be able to observe a large part of the sky and find that interesting transient. It has to have a large aperture, large mirror or lens so that you can actually see faint objects. It has to be able to monitor these things regularly. It has to be able to respond fast. And finally, you also want to automate it. Okay, you don't want a human in the loop. Now, this sounds counterintuitive. Why would I not want a human in the loop? Well, the first time you get a phone call from one of your colleagues at 3 a.m. saying, hey, there's this new supernova explosion, we really should start observing it. You're very excited. You get up, you run, you start observing. When it happens for the 20th time, you're like, yeah, maybe I'll look at it tomorrow. I'm just too tired today. You will say, okay, wait, you are an astronomer, you really enjoy this? Yes, we are, we do, but that doesn't preclude us being tired. And if you are observing at night and you're tired, you actually can start making mistakes. You have a slower response time. You may type in the wrong coordinates because you didn't realize that. And instead of all of that, you could actually have a computer that takes care of all of that for you. And that would just make things a lot faster. It would also make things more accurate. But the third and most important thing is that the job of the scientist is not to just press buttons, right? The reason where you need a scientist is that she or he are going to be creative. They are going to understand that data. And in order to be able to understand that data, you want them to be fresh when they are looking at that data. So if they are sitting up all night just waiting as the telescope is taking data as it is collecting images, then that's not going to be the best use of their time. So with all of this in mind, we set up the Growth India telescope. So this is what we have. This is a telescope with a 70 centimeter mirror, and we have a very high quality camera. A curious thing, this camera is about 16 megapixels. A lot of you probably have phones with cameras that are a lot more megapixels than that. But this thing is many times more sensitive than your telescope's camera, than your phone's camera. This combination together allows us to see things which are about 15 magnitudes fainter or about 1,000,000 times fainter than what we can see with our eyes. So that's the Growth India telescope. It is a wide field telescope, as I said. So what does wide field mean in context of telescopes? So let's compare a few Indian telescopes. I have the full moon here for scale. We can start with, say, the 1.2 meter telescope at Mount Abu. One of the instruments can image about this much of the sky. Remember, the full moon is about half a degree. With the Himalayan Chandra telescope, which is a 2 meter telescope, it can see a slightly larger part of the sky. The current largest telescope in the country is a 3.6 meter Devastal optical telescope, and with modern technology and larger detectors, they actually can cover a respectable size now. But as compared to all of these, Growth India telescope actually has a far larger field of view. So we can very easily tile large parts of the sky. So to put that in context, in a single image, we can see as much part of the sky as, say, the Devastal optical telescope, the 3.6 meter telescope. They would have to take 9 to 10 images to cover the same part of the sky. Right? That means we can just look for things far faster. Here's an image of the telescope inside the dome. There are a few things I would like to point out here. First is that the dome is open in daytime, which is why the telescope is actually pointing here. Imagine the telescope, this has a mirror here. We use a mirror to focus light. So it is essentially like a giant lens. Okay, imagine having a lens that is about this big and accidentally pointing it to the sun. A lot of things are going to catch fire. So if we ever have to open the dome slit in daytime, we make sure the telescope is pointing the other way. This is on the early days when we were actually calibrating the telescope itself. So it has an eyepiece on it. Usually we don't have this eyepiece. We have an instrument here. And you'll also notice that there is no comfortable place to sit in this dome. There's a plastic chair which is meant to be carried away at the end of the day. And the reason is this is robotic. We don't sit there to observe. The telescope takes care of those things by itself. Here's the site. This is Mount Saraswati in Hanle in Leh. Beautiful site. But apart from the natural beauty, it's extremely important for us is that it is at 4.5 kilometers above sea level. The sky is extremely clear, far away from large cities. It means there's not a lot of dust in the sky. It also means there's no light pollution. A lot of you might be from large cities, and when I showed you the Milky Way at the start of the talk, you might have thought it's been a long time since you have seen anything close to that. So clearly, when you are setting up a very sensitive telescope, you don't want it to be that way. The site is shared with several other astronomical facilities as well, and they are all maintained by the Indian Institute of Astrophysics in Bangalore. Here's the first image that we took. Okay, this is first light. It happened in June 2018, so about 3.5 years ago. Some of you may notice this image or recognize this image rather. This is a black and white version. You may have seen a very famous picture called Pillars of Creation taken by the Hubble Space Telescope. This is usually rendered in yellow and blue. So this is what we observed. I would suggest that if you go to this website, which is, or if you just look up Growth India Telescope, then on this site, you will be able to see a lot more pictures and images of the telescope and pictures taken by the telescope as well. All right, so going forward with growth, the Growth India Telescope was set up with the sole purpose of studying transients. Okay, the entire focus is on time domain astronomy. And now I'm going to take you into a little depth into how we actually do science with all of this, right? What's the process and everything. So it starts with what we call the trigger. Okay, either you or one of your friends or collaborators or someone has seen something happen, and they told you, hey, there's something happening interesting in that part of the sky. Go start observing. Once that happens, the first thing you have to do is you have to come up with an observing plan. What else are you observing? Do you want to interrupt that and start looking at this? Is it an exact point object? Do you want to take only one type of images or images in multiple filters? Do you want to tile or cover a large part of the sky and so on? You also have to think about being a part of the network. Do you want to do coordinated observations? Are there colleagues who could do certain parts of it better using their telescopes? Where are the strengths of your telescopes and where would they get used most effectively? Then after that, you actually take those observations, you have your images, you have to process them. Not just for making pretty pictures, you want to process them so that any artifacts are removed. And then you have a nice image, you are seeing a lot of stars in that. Okay, so what's next? Which of these stars is the object of interest? So for that, you need to have a reference image, an image which was taken typically by another telescope or by your telescope, but maybe several months ago or several years ago. And then you have to compare those two images to see what has changed between them. Okay, so with that, you detect this transient, and after transient detection, there are a lot of false positives. There are a lot of things that seem to have changed, which are only artifacts in imaging. And then you might say, hey, wait a minute, you're sitting on the state of the art telescope. Why are you still talking about artifacts? That is because we are looking at very, very, very faint things that are a million times fainter, as I said, than what we can see by the human eye. And that means that any small change that is in data, we want to look at it seriously. We want to see, is this something that I can discard as an artifact, or is it something that is real and that is telling me something about what's happening out there in outer space? And then finally, because of all of this, we keep a human in the loop at the end of it. It turns out that computers are only as smart as you train them to be, which means that if you have programmed your computer to do all of these steps, starting from here, going all the way to here, it is only as smart as you were on the day you did your programming. And if something new has come in, you can actually spot that new pattern far easier as compared to the computer. So there's always a human at the end of the link. Okay, and for all of this, the philosophy that we opted for the Growth India Telescope is that all the repetitive tasks, making the schedule, taking the observations, image processing, comparing it with older data, these are tasks where I know exactly what is to be done, and we want to leave all of them for computers so that the humans are free for the creative part, the science, the progress of science that needs to happen. So how do we do that? Well, here is hidden behind the window at the top is my PhD student Harsh, and he has just sent a command, and you can see the Growth India Telescope again in an open dome in daytime that responded. This is an old video, so you'll slowly see the dome moving as well. and I leave the video running here. But this is not how we usually operate. Usually, instead of Harsh sending this command in a terminal, we have a machine that itself decides where it wants to go next. And a code running on that machine is actually going to start sending out those commands. Meanwhile, here you can see the dome with older motors very slowly catching up to where the telescope pointed. These days, it happens much, much faster. Okay, and this ability to send commands remotely, this was done from IIT Bombay for this particular video. This ability to send commands remotely and is what actually allows us to operate the telescope very, very easily and very conveniently. So of course, took a lot of effort to make sure that all of this worked flawlessly. A lot of students from IITB and the full team from IIA Bangalore worked quite hard to make all of this happen. So here is what actually happens behind the scenes. I showed you one flowchart and walked you through it, and that was already quite a mouthful. So there's no chance I'm going to walk through all of this. But I'm showing this to emphasize that there are a lot of precise steps that need to happen in order to study things which are happening far out there in the universe. There are cases like one of my favorite transients, which I'll talk about soon, where people have waited for 10, 20 years for something like that to happen. And when it does finally happen, you want to make sure you're getting all of your data correctly with no mistakes, because you'll never know when the next chance might appear. So for all of these reasons, computers are very good at doing these repetitive tasks very precisely, and we have automated all of this. All of these boxes actually have corresponding software written for them, and all of those software has been written by undergraduate students, master's students, and PhD students. Okay, so here is a more human readable summary of that flowchart. In the daytime, we sit and make a list of targets, saying here are a few interesting things that we want to study tonight. And in the evening, the telescope looks at that list and starts observations by itself. It calculates the schedule, what order should it observe things in. You want to make sure that you observe targets when they are high up in the sky, not very close to the horizon. You want to observe targets which are higher priority, and so on. Then the data gets downlinked. It gets actually uploaded from Hanle to a direct satellite link that has been provided with ISRO, and then gets downloaded to Bangalore. From Bangalore, it comes over here to IIT Bombay, and our computers here start processing all of that data. So in the morning when we get up, we directly look at the results of all of that processing, and we start our work on the interpretation. Okay, so all right, we came to this with the buffet, right? So let's switch back. What did we actually eat at the buffet? Where, of course, what I mean is that what did we really see with Growth India telescope? But what we saw is also not quite as important. What is really, really important is what did we actually learn about the universe by doing all of this? So what are the results from Growth India? And I'll show a few of them, and we can discuss more in the questions later if any of you are interested. Okay, so I said that I've kept aside, yes, and here's the team. Here's the current Star Lab team. This is my group at IIT Bombay, the Space Technology and Astrophysics Research Lab. And you can see that a lot of them are undergraduate students, and they are the ones who actually do all of this stuff. Okay, so I kept my favorite transient for now. Okay, so what you are going to see here is an artist concept. This is the transient where people actually waited 10, 20 years for just waiting for this to happen. And this is an event that happened on 17th of August 2017. What is shown here are two neutron stars. So these are stars which are made entirely of neutrons. So these stars would be, say, about the size of a large city, 30 kilometers in diameter, but they weigh maybe 1.5 to 2 times the mass of the sun. And when I start the animation here, what you're going to see is that these two stars will orbit each other, and in the process, they're emitting gravitational waves, losing energy. So here we are. The two neutron stars, as they are orbiting, what is shown in blue are renderings of gravitational waves. They don't actually look blue, and that makes the neutron stars come closer and closer. There's a massive collision at the end of it, and there's a huge explosion. Large jets are launched. A lot of stuff is thrown out. This is called ejecta. And this actually is accompanied with a lot of bright emissions in X-rays, in radio, in optical wavelengths, in all wavebands. Okay, All of that stuff that you saw that got thrown out is actually something, this sounds really boring, but this is extremely important for a variety of reasons. Um, for example, you know that there are a lot of elements around us. Most of you will have seen the periodic table. If I ask you what is your favorite element, then answers fall in two categories. Okay, the ones who are science minded and have been thinking a lot about this today will probably name something like oxygen, but the vast majority of us would probably name something else, probably like gold. Now, all the carbon, nitrogen, oxygen, and so on Earth were created in the course of low mass stars. So stars which are maybe something like the sun. But all the gold and the platinum and the silver that we have on Earth was all actually created when neutron stars collided. Okay, and that you saw that material being thrown out. That is what spread through the galaxy, and then the sun and the solar system were formed through the ashes of such stars, and that is why we even have gold on Earth. So what we do is that we take GIT, the Growth India telescope, and we use it to study EMGW, the electromagnetic counterparts of gravitational wave sources. In 2017, when the event happened, Growth India was not operational. As some of you may remember, I said that we had first light in June 2018. And after that, LIGO has been observing again, and there were several neutron star mergers that have been detected by the gravitational wave detectors. Unfortunately, neither Growth India nor any of the other telescopes all around the world could actually find any light coming from those. Most likely reason being is that they were fainter and further away. But let's talk about what we actually did do for these kind of events. What kind of searches did we do? So I'm going to talk about one particular event. We often name these transients events as dates. So S190426 means that this is an event that happened on the 26th of April 2019. Gravitational wave detector said, hey, we have just detected the merger of two neutron stars. And this is where it is on the sky. Okay, so what is shown here as a globe is the map of the entire sky. And you might notice that this looks quite odd, right? There's a large banana shaped region here and there's a darker spot here. The way these gravitational wave detectors actually figure out where the source is very similar to how you hear things and figure out where the source of sound is. So the way your brain does this is that it takes the signal from both of your ears and does rather sophisticated signal processing and says that, okay, maybe if I heard the sound here slightly before I heard it here, it must have come from this side. So this triangulation business is similar. So what we, and in this image, the darkest regions here are where the source was most likely to be located, but you can see that this is spread out over a very large part. So that's where bringing in your friends help. What we decided is that our colleagues at the Zwicky Transient facility would study this part of the sky, and we would focus on this region near the North Pole. This is again where the large field of view of Growth India telescope really matters. So this is what is shown here as this gray outline plus this location here are the parts of the sky that we imaged with Growth India telescope. And to give you context again, this green dot that just appeared, this is the size of the full moon. And this is the size of a typical telescope's camera, the region that it can actually see on the sky. So having this wide field is what actually allowed us to image such large part of the sky. We are the only telescope in the country that can do that. What did we find by doing all of these studies? So this is the kind of stuff that we actually use in our plots, in our analysis. So what we see is this is the image that we obtained in April 2019. This is an archival image. And when you subtract the two, you get a residual here. Or even by eye, you can see that this object in the yellow circle appears to be brighter in our science image as compared to the reference image. It's a bit more obvious in these later cases. So we found 5 of these objects. And what I'm plotting on the right now is on the y-axis is brightness and on the x-axis is time. And these dots, the red dots that you see, are the brightness of each of these respective objects measured as a function of time. And you can see that all of them remained more or less constant. And these colored bands here are how you expect the brightness of any kilonova or any of these gravitational wave sources to change over time. So what it means is that we found 5 new transients, 5 new sources in that part of the sky, but unfortunately, none of them are actually related to that particular event. Well, so was our search all in vain? Well, this is something that is extremely important in the progress of science. Even non-detections matter. So I showed you just 5 events, 5 candidates that we found there, but it's not just those. It also means that we did not find anything that could have been like a kilonova. And what is plotted here with each triangle here shows how bright a source could have been with us still missing it. And those various colored bands again are different theoretical models. So let's look at this case. Okay, if 2 neutron stars had merged, then as per a particular theoretical prediction, this is how the brightness would have changed with time. And you can see that for a couple of days, this band is above our green triangles, which means that the source would have been bright enough for us to see it. The very fact that we did not see it means that this model cannot be true. So even with non-detections, we can actually start eliminating certain theoretical models, saying this is not what could have happened. It must have been one of these other theoretical models. All right, so that's it about the electromagnetic counterparts. Now let's switch to one more science goal that the Growth India telescope focuses on. And this is asteroids. Okay, so I'm sure you have heard the word asteroid somewhere. Most asteroids sit in a belt between the orbits of Mars and Jupiter. Very loosely speaking, they are large rocks floating out there in space. Okay, the largest of them have now been reclassified as dwarf planets. They can be thousands of kilometers across. The smallest of them are can be pebble sized, and you see them as meteors in the night sky sometimes. But what is of interest to us is something called near Earth asteroids. So these are asteroids that could actually come near Earth. And what is being shown in this animation here is every 10 years, many more of these have been discovered. And now you can see that as a few years ago, there are a lot of these asteroids that actually could come near Earth. So I'm going to play this animation again. What is shown is the orbits of Mercury, Venus, Earth, and Mars, and a lot of these asteroids again. So let's go back and look at that. So notice that about 20 years ago, there were only a few near-Earth asteroids known. Near-Earth is classified as an asteroid which actually can pass close to the orbit of Earth. You may say that some of these dots are rather far away. That's because they are not in circular orbit. So they could come in like this, come closer to the Earth and then go out again. As we got better and better with technology and with surveys, we started finding more and more of them. So in say by 2009, we knew a lot more of these. And here you can start appreciating that we are actually in a rather busy neighborhood. So these can come very close to Earth indeed. And if they come so close, then what's to guarantee that they're not actually going to ever collide with Earth? And this has happened in the past. A long time ago, there was a nice, pretty Earth with clear blue skies and lush green forests, and these amazing animals called dinosaurs. And at one point, the universe said, "Nope, your time's up." So a large asteroid came in, hit the Earth, and it wiped out all the dinosaurs. We clearly would not want that to happen. Now, there are actually things like planetary defense where we have as a species reached a technological level where we can actually deflect some of these asteroids potentially, and there are missions like DART which are testing what we could do with those. But the first step in any of this is awareness. We want to know how many of these objects are out there, when are they likely to impact, and so on. Should we really be worried about something that happened to the dinosaurs millions of years ago? Well, it's also been happening since. So let me first show you something that happened on the moon. This is an image of the moon, and in the top square here, I'm going to play a movie part of it again. And what I want you to look at is that you'll see a bright flash happening there. This happened in 2013. So there you have it, one small flash. This flash was caused by a rock hitting the moon. And if you look at that place later, then you see a very nice bright crater here. This was not seen before 2013. It was caused by that impact. And the impactor was not something that was particularly heavy duty. Okay, this impactor was something that was about this big. A rock about a foot in size, weighed maybe about 40 kilos. but the impact, because it is moving so fast in space, it is moving at several kilometers every second. Okay, and the impact was as if you had set off 5 tons of TNT at that place, and it created a crater that's 60 feet in size. That's larger than a typical house. Okay. What else? Well, also in 2013, there was this thing called a fireball that was sighted in Russia at a place called Chelyabinsk. So I'm going to play some news clips here. These are just standard CCTV cameras, by the way, and you can see this object became extremely bright in the atmosphere and then faded out. You can see that it is far, far brighter than the sun itself. Big contrails were left in the sky, and here comes some scary things now. Windows were actually shattered because of this. So this is far more intense than, say, a small meteor that was being seen in the sky, right? So this devastation that it caused, okay, was over a very, very large area. This rock was not even that big. It was about 20 meters in size. Okay, so this is about something that is about the size of a large house, probably. But the energy that it released, it disintegrated in the atmosphere. Some fragments made it to the surface. It fell in a lake. But the energy was about 25 to 30 times the nuclear bomb that was dropped on Hiroshima. And this is something which is about 20 meters in size. I told you that asteroids can be thousands of kilometers across. Let's look at some of these asteroids. So here's an animation again, just comparing for scale. Here's a human 4-meter asteroid. These are not objects which have hit Earth. These are just various asteroids. Now this large one here is about the size of the Chelyabinsk meteor, 22 meters, and they keep, you keep seeing asteroids that are larger and larger. These are still among the small end of the league, right? And you can have asteroids which are hundreds of meters across, and now you can start seeing them in comparison with some of the largest monuments, man-made monuments that you can think of. And if a small one that was 20 meters across could release energy that was 25 to 30 times the energy of the nuclear blast in Hiroshima, you really don't want to be at the receiving end of one of these large things. So what do we do? Well, we actually use the Growth India telescope to study near-Earth asteroids. And we have studied well over 100 asteroids by now. We also again work with some collaborators and scan their data to search for these objects. Then we use the Growth India telescope to confirm them, to measure their orbits, to refine their orbits, and so on. We have actually had some pretty good successes with these as well. Oh, I wasn't supposed to show you this. This is our top secret plan for what happens when we actually find a near-Earth asteroid. Well, these are some students of IIT Bombay who, working with the Growth India telescope, were awarded a special mention by the Astronomical Society of India for the New Discovery Award. And the reason for this award is that they had discovered an object called 2020 QG, which at that point was the closest asteroid, the closest near miss that we had. So this large asteroid flew past Earth about 3,000 kilometers above the surface, but it did not hit us. The record has since been broken, but our work continues. If those faces or some of those names appeared familiar to you, that is because we got a lot of media coverage at that time. You have likely seen a picture like that, or you have probably seen news articles like this. Some of them claimed that the asteroid ruffled Earth's gravity, which was not quite true. But this is our work with near-Earth asteroids. Here are some other asteroids that we have studied. Here's what an asteroid appears like. It appears just like a point. The green circle is there just to show you what to look at. This is an inverted image. So the black objects are all stars, and you can see the clock and the date put at the top. The asteroid is moving across the stars because it is moving with respect to us. Okay, so this is an asteroid GALT. We have actually published refereed papers from this set of observations, studying the properties, measuring its rotation, and so on. GALT is a main belt asteroid that was relatively slowly moving. If you have an asteroid that is closer to us, then the speeds are similar, but it is closer, so it appears to move faster. This is just like looking outside a train, where the poles that are right next to the tracks appear to move much faster. The mountains which are far away appear to move slower. So if an asteroid is moving faster, we actually have to move the telescope with the asteroid, and the stars appear like streaks. So this is again like photos from, say, sporting events or car races or so on, where if the photographer is tracking the car, everything else looks blurred. So the stars behind are actually looking like streaks as we track the asteroid. We also do several other science things with the Growth India telescope, but I want to wrap up soon, and I want to talk about one more very important key goal that was defined by us when we were setting up this telescope, and that is education. So we want to make sure that the next generation of students are actually learning how to do these advanced astronomical observations and analysis and so on by using this telescope. You have already seen the Star Lab team, so I won't show you the same photo again, but we have more than 40-50 students who have actually done research projects on this, and hundreds of students who have learned through summer schools and workshops, and we continue to increase that number every day. What I'm going to show you next is something that we have done specially for National Science Day 2022. So what we did, you may have heard about something called the James Webb Space Telescope. It was a very advanced space telescope launched by NASA several months ago, being touted widely as the successor to Hubble. And we wanted to show you a glimpse of that telescope. So here's what I have. This time I'm not inverting the image. So all the white dots are stars. And this square here is shown as a close-up here, and you can see there is a white dot that is moving through the center of the square. So this actually is the James Webb Space Telescope as imaged by the Growth India telescope, and today is the first time we have actually released these images. The animation here was done by Harsh, a PhD student here. So just looking at James Webb Space Telescope, wow, that sounds like fun. You know, it appears like a point. You can see that it's really out there in space, but that's not enough. We wanted to do more with it. So we actually contacted our growth collaborators in Taiwan, and they went and looked at it with the Lulin optical telescope, and they also saw it moving. Okay, and these are actually data taken at the same time. And you'll notice that there is something quite interesting happening here. As seen by the Growth India telescope, notice that the background stars are the same. We saw the James Webb Space Telescope here, whereas the Lulin optical telescope actually saw it here. And this is called parallax. It is, suppose you hold your finger out in front of your face, and if I close this eye, then I'll see a different background for my finger. Whereas if I close this eye, I will see that the finger appears to have shifted. And by using this, we can actually calculate the distance to the telescope. And this is something which we regularly teach in astronomy classes. So these images are actually going to be used for that in the next semester, next year when we are teaching this course. And we actually verified that James Webb Space Telescope is indeed orbiting at 1.5 million kilometers from Earth. So these are special images that we obtained just for today. And before I close, I would definitely want to thank people that make all of this possible. The telescope itself, as I said, was jointly set up by the Indian Institute of Astrophysics, Bangalore, and IIT Bombay, with funding from the central government, DST-SERB, and the Indo-US Science and Technology Forum. And more recently, to continue operations of the telescope. Setup is one part, but you still need to keep maintenance and upkeep and upgrades. And all of that has been made possible through a very generous donation from the IIT Bombay alumni batch of 1994. So we want to thank all of these people for making this research possible. You're all awesome. And I'll end with that, and we can take any questions. Thank you.
Thank you, Professor Varun, for the wonderful talk. So we have questions both in our Zoom and also in YouTube. So I'll read out the questions to you.
Sure.
And the audience can again post questions. Okay, I'll take the first question. This is from Neil. Are triggers identified automatically, or is it a manual process? If it is automated, can you tell how the trigger detection works?
That is a very interesting question, Neil. So the question is about when I said we find transients, we start with a trigger. Triggers can actually come from various sources, and they are a mix of automated and manual. So one of the places that generates triggers are space telescopes. For example, this is AstroSat, and AstroSat one of the instruments that we have on AstroSat is the cadmium zinc telluride imager. It detects these explosions happening in gamma rays. But AstroSat data is something which we look at manually to verify that what it detected is indeed a GRB. So that would be a manual trigger. But the trigger is then sent out over a machine readable protocol over the internet. So we send it in such a way that other computers can directly interpret it. And there are other telescopes which can actually generate those triggers automatically as well. In addition, there could be other optical telescopes. So if I am doing my own thing tonight and I discover a supernova, I will issue a trigger. So that trigger generation again would be manual. There are other space telescopes for, and there I dropped it. That would have been so this is a model of Daksha. This is a proposed space telescope that we are making. Don't worry, I'll be more careful with the real one. This is something that is being designed to be 10 times better than all the existing telescopes that generate gamma ray bursts. So, the current world leading missions are, there's a NASA mission called SWIFT, there's a joint NASA-ESA mission called Fermi. This will be a fully Indian mission that will be 10 times better, and it will also automatically generate triggers using very sophisticated onboard computing. I hope that answers your question.
Thank you. Now, the next question is from Shubham. He asks, how having a small aperture growth telescope captures wide view pictures?
That is interesting. So aperture is basically the size of your mirror or lens. And in one of the slides here, I had shown that, okay, let me jump back to that slide. Okay, so as compared to other telescopes, Growth India is just 0.7 meters, whereas these are much larger telescopes. What happens usually is that as your lens becomes larger, your field of view, your magnification also ends up increasing, and your field of view typically becomes smaller. That does not seem to be the case when you look at these three telescopes listed on the right. The reason for that is newer technology, actually. So with newer technology and larger detectors, these newer telescopes like the Devastal Optical Telescope or the Himalayan Chandra Telescope got a bigger field. But in general, the field of view of a telescope more or less is inversely proportional to its aperture. Intuitive way to think of it is that your eyes have small lenses, so you can see a very large part of the sky or anything around you. If you look at binoculars, you will see something that is narrower. If you use a DSLR with a zoom lens that is a larger aperture, then often you'll see much smaller things. And if you look through a telescope, you see even a smaller part of the sky. So having a smaller aperture actually works in our favor. But even for a 0.7 meter telescope, there's a special optical design that we have called the corrected Dahl-Kirkham design, which enables us to get a wide field of view. That was a requirement that we had.
Thank you. Now, next question is from Gauri Shankar. He asks, how light is produced by chargeless neutron?
How is light produced by the chargeless neutron? That's a good question. I think this refers to when I said neutron star collision, which emits a lot of light in different wavelengths. When the neutron stars collide, okay, it is complete chaos. So think of it this way. You may have all heard about the Higgs boson. Okay, this was a discovery that won the Nobel Prize and so on. How was it discovered? In a particle accelerator, we took protons, essentially accelerated them to very high energies and made them collide with each other. And in the collision, it created all sorts of particles which were not originally, which was not what we started with. Similarly, in the case of neutron stars, when they collide, it's extremely violent process. And the neutrons by themselves are not very stable. The moment these stars get tidally disrupted, the material spreads out. They actually do get converted into protons and electrons and antiprotons, anti-electrons, all sorts of things. And it is those things which are actually doing all the emission. And in fact, by looking at the spectra, so it's a bit more technical, so I didn't go into it today, but by looking at the data through a spectrograph, we can actually even tell what elements have been created.
Yes, thank you, sir. Next question is from Hemanta. Experimentally, how to confirm that we are receiving light from a particular celestial object? Because the entire universe, there are many stars which may be sending light signals in the direction which we are looking.
Okay, that is actually yes, the universe is full of a lot of sources and they're all emitting light and they're all doing their own thing. But fortunately, this turns out to be more straightforward than we would imagine. Just as if you're standing in a room and you hear someone talk, you can know, first you know it came roughly in that direction, but then you see there and you can pinpoint the location. All of that is happening with triangulation. With light, things become much easier. So if if I take a telescope and I point it to a particular object, I'm getting light from that object. Occasionally, and this happens rarely, what can happen is there can be another object that is extremely close to that in the sky. It need not be physically close. I could have a scenario where I have object 1 over here and I can have object 2 over here. Okay, this is much farther away, but as seen by you, they could actually be right next to each other. And we can calculate the odds for that. It doesn't happen very frequently, but we do have to worry about it. And in those cases, we have developed certain techniques, again, based on spectroscopy, or we can go to larger telescopes to obtain higher resolution images to make sure that what we are seeing is actually the particular object that we were interested in and not something in the background or in the foreground. Fortunately, it is not a very, very common occurrence.
Thank you for answering that. Next question is from David Brown. Are the following two statements facts? So the first one is Milgrom Mond has many empirical success. The second statement is Mond's empirical success require a new paradigm.
I'm afraid I don't have the context for these questions.
Yeah, this Mond is modified Newtonian dynamics.
I'm afraid that's outside my area of expertise. So
yeah, sure. I'll move on to the next question. Anupam asks, how do we know where to point the telescope since it has a limited field of view?
Correct. So this is where the trigger comes in. So on one hand, we have instruments like Daksha, which are designed to observe very, very large parts of the sky so that they can find anything that happens there. In terms of ground-based optical telescopes, the Zwicky Transient facility has the largest field of view right now. And what they do is that every 2 minutes, they'll point to a different part of the sky, covering 42 square degrees at a time. There is something called the Vera Rubin Observatory that's being set up in Chile, should become functional in a few years. They are going to conduct a survey called the Legacy Survey of Space and Time, LSST. And that will be another telescope. So we just keep looking. Think of it as if you are a sentry or a watchman outside a camp, where your job is to warn your friends if you see a tiger coming. So you'll just keep looking around, and that's what we do. On AstroSat, one of these instruments mounted on the side here, this is the scanning sky monitor, and that has the same job. So it can actually turn, and these instruments point to different parts of the sky. So we have to keep searching for these triggers. And sometimes with all sky telescopes, sometimes with pointed telescopes, and then only then can telescopes like Growth India go and start following them.
Yeah. Anupam again asks, is the gold metal created only when heavy stars collide?
As far as we understand, all the gold in the universe actually came from collisions of neutron stars, not just any heavy stars colliding. They can cause other things called luminous red novae, for instance. But in particular, neutron stars colliding, as per our best understanding, and a lot of this understanding came from studying the August 2017 event. Until then, it was just a hypothesis. So yes, all of that was made in neutron star mergers. Now, that also tells you what a crazy place the universe is. So with the Big Bang, there was mainly hydrogen. And from that hydrogen and a little bit of helium, the first generation of stars was born. Those stars lived their lives, evolved, died, and they created neutron stars. Okay, or actually they created second generation stars, which would then be lighter, and those in turn would create neutron stars. And then you have to kill those neutron stars again, by making them collide with each other, and that is where the gold is getting manufactured. Then it is spreading out through the galaxy, and the sun and the solar system are now born from the ashes of those stars. That's, this sounds like the script of a really over the top Indian movie, right? But that is just how the universe is.
Thank you, sir. Next question is from Professor Ajit. What is the estimated rate of asteroids colliding with Earth?
So the okay, the answer to this depends on what we are looking for, right? There are a lot of asteroids that collide with Earth every night, because we clearly see meteors every night. Even if you if I go back and play the movie that I showed you, so let's do that. Even in that, you are going to see asteroids. You are going to see meteors basically. And if you keep see, there was one that just flashed here, and if you keep looking in that part, you'll see a few more. So very small objects we get to see very often, but as you get to larger and larger asteroids, these collisions become more and more rare. So objects which are tens of meters in size seem to impact us once every decade maybe, and kilometer size object or okay, so there you saw a whole bunch of meteors right now flashing past, and there you have them again at the top. So these are all small asteroids. Objects that are roughly about 140 to 150 meters in size or larger are objects that could potentially end civilization, and those seem to be rare enough. They will occur once in thousands to tens of thousands of years, maybe even longer than that. I don't know the exact stats on those. And it means that we will be able to actually hopefully identify enough of them well in advance, and we will hopefully have the technology to deflect those so that they don't wipe us out.
Thank you, sir. Another question is from Umesh. Why does gravitational wave travel at the speed of light?
Ooh, that's a interesting question. So yes, gravitational waves. So let me give context for everyone. Gravitational waves are a prediction of Einstein's theory of relativity. And when I showed you that animation of two neutron stars colliding and they emitted gravitational waves, those waves actually do travel at the speed of light. And this is a prediction of Einstein's theory of relativity. Okay, the theory of relativity postulates that there exists a special speed, and that speed happens to be speed of light. That's the speed at which light travels, but that is also the maximum speed at which any disturbance in space-time itself can travel. It is a consequence of Einstein's equations. Beyond that, unfortunately, we don't have an answer to why. Okay, we could ask a question as to why did Einstein's equations not predict speed twice that of the speed of light for gravitational waves? And this endless succession of whys is actually what drives science. So maybe someday a grand unified theory will pop up which will tell us why those equations actually yield the same speed for gravity as they do for light. But as of now, that's all I can say. Maybe Ajit can add something to this.
No, that's all we can say right now. I agree.
Okay.
Yeah, thank you. Next question is from Letika. What accelerates asteroids to leave their orbit and travel this far to Earth or Moon?
So this is interesting. Good question. So let me go here and let's go to that asteroid slide again, because there's an important observation there, which is, are those asteroids really out to get us, or is something else happening? Okay, so the asteroids that you will see on this slide, let's play this. Okay, you notice that they are not quite heading for Earth by themselves. They are just going around the sun doing their own things. The major planets all happen to be in circular orbits, but the most famous dwarf planet, Pluto, is itself in a very highly elliptical orbit. You'll see that the blue dots here are all near Earth asteroids. The brown dots, which is the big cloud that just appeared on screen, are all regular asteroids. So most of those regular asteroids are in a more or less circular orbit or a low eccentricity orbit, technically speaking, around the sun. But a very small fraction of them does happen to have orbits which are more eccentric. Some of them may just have formed in orbits like that. Others, when two asteroids go past each other, they are the gravitational force that acts on them, each other's gravitational force is going to slightly deflect their orbits. I also showed you this animation of 2020 QG2. Let's see, where was that? I think it was this one. Nope. No. This one. Right. So this asteroid, it came in along a straight line from the right side of the screen, but then Earth's gravity deflected it. So anything that is passing by any other massive object, the orbit will get deflected. Some might have been just born in orbits like that. So that gives them elliptical orbits around the sun. They don't particularly care about Earth until they come close enough for the Earth's gravity itself to impact their paths. And just because there are so many of them, there's a chance that they will occasionally come and hit Earth.
Yeah, thank you, sir. Next question is from Pranav. Does the Growth Telescope have applications in cosmology?
Yes, indeed. We have just published a bunch of papers about supernova analysis, which all have cosmological implications. So one of the goals is to study supernovae. Supernovae are used for cosmology. The other key goal is to study GRBs. Gamma ray bursts themselves have been used for cosmological studies, in particular metallicity variations across redshift, for instance. Yet another goal is or a key goal is in fact to study the electromagnetic counterparts of gravitational wave sources, which give us an independent measurement of the Hubble's constant. So yes, the Growth India telescope has a lot of applications for cosmology.
Thank you, sir. Next question is from Rahul. He's asking, what is the size of a planet killer asteroid?
A planet killer would be something that's about 140, 150 meters in size. If you look at the crazy movie idea of planet killers, including Star Wars and stuff, the idea is that something comes, hits Earth, and Earth itself breaks into two. That's not what will happen. The planet by itself won't really suffer a lot if a 150-meter asteroid hits us. What will happen though is that it will create massive tsunamis, and it will create something akin to a nuclear winter. It will throw up a lot of dust in the sky, and that dust will take years and years and years to settle down. And which means that there is not enough sunlight that reaches the surface. So the tsunamis first and earthquakes will wipe out a lot of things. Whatever survives from that, there will be no food growing for many, many years. And because of that, everyone will unfortunately starve to death. So technically they are civilization killers, but yes, the common wording is planet killers. Those would be 140 meter plus in size, roughly.
Thank you for answering that. Next question is from Gauri Shankar. How distance between two stars and planets in space is measured, as all photos are in 2 dimensions? How mass of stars and planets are measured accurately?
Okay, so multiple questions here. One of those I happen to have a nice demonstration for answering. So let me show you that one, which is, this is how we actually measure distance. Okay, so if I have two telescopes that are separated by 4,200 kilometers, they observe the same object. The other stars we know are much, much further away, so they don't seem to move. This thing appears to move and it shifts. If it was much closer to us, the shift or the parallax that is marked here would have been larger. So if Growth India saw it here, Lulin would have seen it even further away, maybe somewhere here. If it was further away, then the parallax would have been less. So this parallax allows us to measure distances. As things get further and further away, distances become harder and harder to measure. The full answer would get a bit technical for everyone here. So I would rather suggest that you look up something called the distance ladder in astrophysics or in cosmology, which is how we measure things, distances to things which are further and further away. How do we measure masses of planets? To measure masses of stars and planets is actually quite difficult as well. And the way we measure them is by trying to measure the effect of their gravity on their surroundings. So if I have a planet, it is going around a star. And Newton's law, which you will have studied at some point in school, is that gravity between two objects is gmm by r square. So the m and m are masses of these two objects. So if I study how these two objects, the planet is going around a star, how they're interacting, or if I have a binary star, how they're going around each other, then that actually allows me to measure masses of those two objects.
Thank you. Next question is from Siddhi. He asks, are we studying stars just to understand our universe better? But how will it benefit us if it is just for our curiosity to know more?
Okay, that's a very deep question. So I'm going to answer it at various levels. Okay. The first part of the question is, why do I study stars? I study them because I like it. Okay. It is like asking, why did Lata Mangeshkar sing? She sang because she liked it. And others happened to like it too. But she wasn't exactly building buildings for people to stay in or growing crops for you and me to eat. Okay, so not all endeavors should be measured in terms of what they do to us today. Okay, this is part one of the answer. The related part to that is that it is this curiosity which actually separates us from the rest of the animals. Okay, this is finally a quest about origins, where we came from, and that is what has driven us to build new things, to invent new things, to develop new technology, and that is the technology that we are using so easily right now. Okay. Einstein's theory of relativity, both the special and general theory, are something that you and I unknowingly use every single day now. Back in 1905 to 1915, when Einstein was working on relativity, he was trying to figure out there's something weird with Maxwell's equations. Why does light have a constant speed at all? And then he asked a question very similar to one that one of you asked 5 minutes ago, which is that how exactly does gravity work? And in trying to answer those questions, he was trying to understand something which is rather esoteric for most of us in our daily lives. He was trying to understand what is the nature of space. So how does it matter to me today? Well, you probably have a GPS in your phone, right? You've probably used it to order pizza one night when you're hungry, or to call a cab. The GPS, the way GPS works is that there is a network of satellites that is orbiting the Earth, and these satellites essentially send out a beep, 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 beep signal, and your phone detects that signal. Okay, it also uses some other things for triangulation, but I'm talking only about the GPS part here. Your phone detects this signal from 4 satellites, and it uses the time of arrival of those signals to figure out where on Earth you are. Now, in doing so, it actually has to account for the effects of special theory of relativity and the effects of general theory of relativity. If you don't account for that, okay, if you linearly extrapolate by just one day, then the positions will be wrong by about 10 to 11 kilometers. So you order a pizza and some unknown person staying 10 kilometers away gets it, right? When Einstein was doing this, he was trying to understand how the universe works. 100 years later, okay, that curiosity about how the universe works has led to you being able to order pizza at home and to get a cab without leaving where you're standing. So the spin-offs from these technologies can be immense. The technological spin-offs from these pursuits can be immense, but they don't come right now. And we don't know which of these explorations is going to lead to a spin-off later down the line. That is why we have to pursue fundamental research. And finally, a third answer to that is that there are technological spin-offs that come today. For example, the telescope that you are seeing streaking across the screen here is the James Webb Space Telescope. In order to measure the optical quality of James Webb Space Telescope, they had to do some new fast optic stuff, which actually is now used in LASIK surgeries. Okay, lasers being developed for LIGO India are improving laser technology across the board. In a few years, we might see applications in industry and in medicine. The detectors that we will use on Daksha, or the ones that we used in Astrosat, the cadmium zinc telluride X-ray detectors, actually are used in hospitals to take X-rays when someone's bone is broken. So there are a lot of technological spin-offs that come from science. So anything that we are doing here is a free exploration, and it should be thought of in that sense, because without that free exploration, we will not make these breakthrough discoveries which will actually allow us to then create new technologies which everyone eventually will use in their day-to-day life. So very good question, and this is why we do.
Thank you, sir. There's another question from David Brown. Is it possible that there exist asteroids that consist primarily of dark matter particles?
That's an interesting question. So there is some, for context for everyone, the universe seems to have a large amount of what is called dark matter, 5 to 6 times more dark matter than normal matter. In fact, the kind of matter that you and I are made of. From what we understand of dark matter so far, and it is based on circumstantial evidence, is that dark matter cannot form very small or lightweight clumps. This is what our understanding as of now is. There were initially ideas about dirty snowballs and so on, where you could have lightweight dark matter clumps. But what we understand now is that they seem to be at least galaxy size or fraction of a galaxy size. So stuff that is weighing thousands of times more than the mass of the sun would be the smallest dark matter clump that you could have. And we definitely don't have anything like that lurking in our solar system. So as per our current best understanding, we cannot have dark matter asteroids.
Thank you. Next question is from Shubham. How actually telescope or people working there recognize that the particular object being observed is the only point of interest?
Okay, so let me again answer in 2 parts. First part is that we have to figure out where we are pointing. For example, if I look at this image that you see in the background by looking at all of these stars, we compare it against a database of stars, of positions of stars, in a process called astrometry. And that tells us exactly which part of the sky we are looking at, where each of these points is. Beyond that, the next part of the question is, how do I decide which of these objects is actually interesting? And the answer usually is that we don't know, which is why we have to automate all of these processes, because in this image itself, you see hundreds of stars, and this is one image, okay, or in this case, about a dozen images that we took one after the other to make this animation. But we take 50 to 100 images each night. Each image has thousands of stars, and we cannot manually go through all of them, which is why we write these sophisticated software and algorithms and programs that will compare these stars, look for whatever properties that are of interest to us, and on the basis of that, we will identify what targets are interesting. Taking a step further back, it begins with defining a science goal. I want to explore these kind of properties of objects, and that has to be loosely defined, because if you know exactly what you're looking for, it means that somebody has probably already studied. So no point in doing exactly the same thing again. So you go and try to find these, you define something called your science goal. On the basis of that, you actually have to propose to get telescope time, saying, I would like to point my telescope at these parts of the sky because I hope to get the following information from objects in those parts of the sky. And then you go ahead and analyze that data.
Yeah, yes. Thank you, Professor Varun. Actually, we are done with almost all the questions, both in YouTube and Zoom. I think I have taken all the questions which are relevant to the talk. Yeah, so once again, I thank you for your wonderful talk. And also I thank all the audience present here. Yeah. And is there any other question? We have a few more minutes. So we have one more question. What is the status of LIGO India?
LIGO India is proceeding. There's a lot of behind the scenes activity that is going on actually. So for those of you who don't know, there are currently the discoveries that I talked about were done with 2 LIGO detectors in the US and 1 in Italy. There is a detector that is being set up in India in a place near Hingoli in Maharashtra. And the land has been acquired, construction has started there. There's a lot of behind the scenes activity that is happening in more than a dozen institutes across the countries. IITs, ICERs, various research institutes, including our host today, ICTS. are working on different hardware aspects, data processing algorithms, software aspects, and so on. The full details of what is going on would be too long an answer to cover here, but I'm sure that if you look at other Science Day talks organized by ICTS and other institutes today, someone will have covered this in great detail.
Yeah, we'll take one more question. How far or how close are we to the theory of everything? And is it possible to actually achieve it? So is it related to your talk?
That's a very interesting question. And the answer is a part of the thrill of science itself, which is that we don't know. And we really desperately want to know. We want to have a theory of everything, and we want to know how to achieve it, and we want to know when it will come. But if you already knew all of that, then it means that the theory is pretty much there already, right? So we don't know, and that is why there are so many people working hard to crack that question. Do I think we are on the threshold of it? Probably not. But that doesn't mean that there isn't someone toiling away in his or her room right now, working on something for years and years, and they maybe have put something together. Very famous example of this was the proof of, say, Fermat's last theorem and stuff. The person who published it was working in pretty much obscurity for a very long time, many years. And then he wrote it up, and the proof was accepted. And it had been something that had been troubling people for decades. I personally don't think it's going to come tomorrow, but you never know.
Yeah. So yeah, I think we can stop here.
Thank you.
We are done with almost all the questions, and yeah. I thank each and everyone who has joined here.